Well, let's start. First of all, thank you all for coming, especially on Friday. Well, my name is Adrià Torralba. I'm a Ph.D. student at work, here, pretty close here. And today I'm going to do a workshop, and I will try to be interactive, about zero knowledge basics, and in particular we're going to deep dive into KZG commitments, also known as Kate commitments. As I said, if you want the slides, you can find it here. And, well, first of all, why commitments? Well, because they are cool. No, it's a joke, although they are. Commitments are useful, and in particular in the zero knowledge world. And if you're here because you read zero knowledge basics, I assume that you are interested in the field, and maybe you know the ZK whiteboards videos that Anne Rose and her team is doing, and in particular on session 2, Dan Bonnet, a really great cryptographer, explains how to build modern ZK snacks. And well, right now, nowadays, everybody is doing ZK frameworks with a combination of a functional commitment scheme along with an interactive oracle proof. I'm not going to explain what an interactive oracle proof is, but please believe me that commitments are really important. And actually, if you know or if you have heard about Plon is using KZG commitments as its commitment scheme. Another reason why commitment schemes, and in particular polynomial, and more in particular Kate commitments, are important is because they will be used on Proton and sharding, also known as EIP 4844, that will improve the data availability on Ethereum. And they are planning to use, in particular, KZG, because they suit perfectly their needs for, well, or more or less, they suit their needs for a number of reasons. So, this is the article we are going to explain. This is called Polynomial Commitments by Kate, and Goldberg, and this is why this is usually known as Kate commitments, because of the author. Okay. Our goal, and the goal of the article that will be our goal, is to prove, by the way, this is an interactive protocol in the sense that we have two main actors, a prover and a verifier, and the prover tries to convince the verifier about something. And in particular, in this case, the prover will try to convince the verifier that he knows a polynomial written in usual standard form, like this, and which coefficients are in a finite field. More on that later. We're going to try to prove that we know a polynomial without revealing the polynomial, okay? And in particular, we want to prove that we know an evaluation of this polynomial, okay? But, well, before going into the protocol, we need to explain some setup, okay? We will be working on a finite field of prime order P. Please, this is, for the rest of the workshop, if you don't know any of the things that I'm explaining, or it sounds like crazy, please interrupt me and I will try to explain. Okay, this should be like really interactive. Okay, a finite field of prime order P is like a regular field, let's say the reals, is a field, but instead of having infinite elements, you have a limited number of elements. That's all. And we want them to be of the number of the elements, we want them to be a prime number, because prime numbers are really cool and are really useful. Okay? A technicality here is that we ask that the polynomial should be large enough, larger than 2 to the 2k, where k is the security parameter. This is in order to ensure that the randomness that you are running is actually useful and nobody tries to tamper-proof your. The degree of the polynomial that we will be committing will be at most t, and t will be strictly less than p. Okay, so we cannot commit an arbitrary large polynomial. We are limited by this p. Okay, we will assume that we have the generator and we know the generator of the field and also of the group associated with the field. Okay, and in the more theoretical part that is right now going on, we will work over the multiplicative group of the field. Okay, so we will take G star. G star is all the invertible elements on the graph by the multiplication. That usually this is 1 to the p minus 1. Okay, the boring stuff is about to end, I promise you. But I need to say that. Okay. Well, this is the setup, and we also need two cryptographic assumptions. Okay, we will assume that the discrete logarithm in this field is hard, and this means informally that if we have the generator of the group, the generator is an element that, I mean, when you take this element and you multiply this element by itself a number of times, it generates every single number on the group. You don't need any other number to generate. One number and in this case the multiplication, you have all the elements in the group. So a generator G of the group G, and if someone gives you G to the X, also belonging to the field, finding X is hard. This means that it's computationally unfeasible to find it in a reasonable amount of time, usually in polynomial time. We cannot find X this century, let's say. Okay? And another cryptographic assumption we will have is the strong Diffie-Hellman assumption. That informally, this is stronger than the previous one, and informally it says that, again, given a generator, if I give you G to the A and G to the B, where A and B are elements in the field, then G to the A and G to the B are indistinguishable from G to the AB. Okay? This means that if you take G to the A and G to the B and G to the AB, they act, I mean, for random values, they act like three random variables with independent distributions. You cannot guess and you cannot correlate one to another. You don't have any information about the three different elements. Okay? Okay. Enough boring stuff and preliminaries. Let's recall what we want to do. Okay? We want to prove that we know an evaluation of a polynomial. Okay? But without revealing the polynomial. I mean, how can we do that? I mean, it seems like crazy, but yeah, it can be done. And the answer is using commitments. A commitment is an analogy of a real-world envelope, in the sense that it has two really cool properties. The first one is that a commitment is binding, in the sense that once you commit a message, you cannot change your mind later. You are like committed to this message. Okay? And the second one is hiding. The commitment does not reveal the message until you open it. I mean, when you send an envelope to somebody, I mean, the envelope is there and I cannot change it. But if they allow me, I can go and then I can show the message. This is the same analogy, the same idea. Okay, let's start with the protocol. The protocol has 4 different phases. The first one is called the setup. Okay? In the setup, we take K, the security parameter that we will ignore for this talk, and T, the maximum degree of the polynomial, and we will compute two groups G and GT of prime order P. Oh, okay? With KB or security. k bits of security, along with a pairing. But what is a pairing? A pairing is an application E that takes two elements of the group and outputs an element of another group. And we ask the pairing to have two different properties. The first one is that the application is bilinear. This means something mathematically in particular, but in our case we will, well, this is like a simplification. In our case, what we will ask is that if we have e to the GA, GB, we can play with the exponents in this operation as we want. I mean, we can put all together on the first one, all together on the second one, or we can even withdraw them outside of the function. Okay? All these equalities hold. Additionally, we will ask the application to be non-degenerate. This means that if we evaluate E to the generator and the generator, this is not one. This is not the neutral element of the field. Okay? So, going back to the setup. We have T, we have generated two groups, G and GT, of prime order P. P large enough. Along with a pairing, and we know right now what is a pairing. Now, we ask somebody else outside of the prover and the verifier to pick randomly an alpha in the field. And he will compute for us what's called the public parameters, PP. And PP are G to the alpha square, all the way along to G to the alpha T. Okay? It is really important that this trusted party deletes alpha, more on that later. And finally, this outside party will send the public parameters to both the prover and the verifier. Okay, now we have the setup, and we will actually commit. The prover wants to commit a polynomial. So he will run a function, let's say, that computes the commitment. And the commitment, we will define the commitment as C, that is G to the phi alpha. Phi is our polynomial, and alpha is this hidden, random, actually toxic waste that we need to get rid of. But, I mean, how can we compute this evaluation of the polynomial on alpha if we don't know alpha? I mean, it makes no sense. Well, maybe it makes sense. Let's see. Because if we recall, both the prover and the verifier have G to the alpha, G to the alpha square, G to the alpha D. Okay? And now, G to the phi alpha, if we put that in the usual way, is G to the A0 plus A1 alpha plus AT alpha T. And if we rearrange them, we can put like G to the alpha 0 times G to the alpha 1, G to the alpha square to the A2 times G to the alpha T to the AT. But look, I mean, these element are from the public parameters. They are pre-compute. You don't have to compute. You don't need alpha to compute these elements because they are already for you available. So you take this expression and you compute the commitment like this. And you send this commitment to the verifier. And this commitment is a single field element. Okay? Now, we want to open. Actually, the verifier will ask, okay, if you know the polynomial that you have already committed, then why don't you open that at A that I will send you? Okay. The verifier sends I on the field, and the prover will do a clever algebraic trick in order to prove and provide the proof along with the image that he knows the polynomial. Well, we observe that if we define y as the image of the polynomial at I, then by definition, if we define a polynomial that is the polynomial minus y has I as root. I mean, put I here, phi of I minus phi of I is 0. So it's a root. And, well, basic, I don't know, some mathematics from high school, I don't know, says that if that's the case, then x minus I perfectly divides this polynomial here. So the prover will do that. The prover will, this is like formally, there exists a C polynomial that perfectly divides this, it factorizes this polynomial here. But yeah, this means that there exists C on the field of the polynomials here, such that phi of x minus phi of I is equal to this C times x minus y. So this C here is actually this term here divided by this term here. If you put this here, then this and this cancels, and you have the left-hand side. I mean, it's like 101 in mathematics. So if we rearrange this, I mean, we put this on the other side, we have this cool expression, this another cool expression of the polynomial that we have committed, okay? And moreover, this C, the quotient polynomial that we have proved to ourselves that exists, is our proof polynomial. And the proof will be a commit of this new polynomial. So, as before, I mean, this is a polynomial that actually is 1 degree less than the original polynomial because you have divided by a polynomial of degree 1. Then we can define another commitment, that the commitment is actually the proof. The proof is C sub C, which is G to the C alpha. And this thing here will be computed just as before, just as the commitment phase. So finally, the prover will send these 3 elements. We'll send I, phi of I, and the proof, the commitment of the C polynomial. Okay? And now arrives the tricky part, or in my opinion, the most difficult part. That is the verification. Because the verifier has to verify that phi of I is indeed the evaluation of this polynomial phi. Okay? And well, B, in order to do that, has these tools. B knows the original commitment, B knows I, B also knows phi of I, and finally knows this proof, this new commitment. Okay? And with that, well, recall that we have this expression that we have deduced, and well, if this is a general form of the polynomial, this polynomial, well, this identity also holds for alpha, because it holds for every element. So we can have something like that. Phi of alpha is equal to psi of alpha, alpha minus I, plus phi of I. But we don't have this directly. We have values committed, but with G here and G here. So maybe the verifier wants to compute something like that. This is simply G to the left-hand side is equal to the G to the right-hand side. And look, we have this, but we don't have G to the alpha times C. So maybe this seems like a good idea, but it seems that we still need alpha, and nobody knows alpha. Only the trusted party, and then he gets rid of it. So maybe it seems that the verifier still needs alpha, But, well, the answer is obviously no. Why? Because pairings come to rescue. Okay, this is why I explained what pairings are. Okay. Technical issues? Okay. Cool. Yeah. Using pairings, the verifier will check the following. We'll do an operation like this. We'll check, is this part here equals to this part here? And why this? Well, in the article is explained. This is like the most optimal way to check that from a computational point of view. And we are doing this with computers, so we will do that. And here, well, I explained how if you take the right-hand side and you apply the cool properties of the bilinearity of pairings, and you apply them once more, and even one last time, you arrive to the left-hand side. That's all. Okay? So, if I give a commitment, the image of the opening, and approve, and the verifier takes this data, because the verifier have C, have also this, he have G to the alpha, because this is in the public parameters, and he knows that. So the verifier knows every single thing here, so he can compute that. Okay? So if he computes this part and this checks to, and this is equal to this part here, then the verifier will do something like that. Okay? And well, that's about it. This is the summary of the protocol, where at the beginning we have the trusted party doing the setup. He generates alpha randomly and generates the public parameters, and then deletes alpha. He sends the public parameters to the prover and the verifier, and then the prover wants to commit a polynomial. I will pick a polynomial and we compute the commitment using the public parameters. We commit the commitment, and now the verifier asks me to open this polynomial at I. Well, I compute the quotient polynomial and I commit this new polynomial. And I send the image and the proof to the verifier. And the verifier checks if this holds. And if this holds, everything is happy and everything is good. Okay, well, I'm like really tired, so now it's your turn. Okay? And, well, I have an idea. I don't know if this will work, but we will try. What is my paper? Here. This is a workshop because now I explain this boring stuff, okay? And now we're going to do, more or less together, a simple example with small numbers here, okay? And, well, since here we have 3 actors, I will ask 3 people on the public to join me, and I will moderate this. So I need someone here to be the trusted party. Not all at once, please. Come on. Who? You? Sorry, no, sorry. You come later. He raised us before. Come. Please clap. Carlos, I'm Adria. Okay, what is my paper? Yes. Okay, so you are the trusted party. And the trusted party, what is doing? Let's see here. Yeah, so you are going to generate alpha, you are going to compute the public parameters because only you knows alpha, and you are going to delete alpha afterwards. Okay? So, please pick the same alpha that I chose. Okay? Yeah. Thank in order to do like things easy, I picked the following like general parameters. We will be working on F11.
Can you pick another color? Because it doesn't highlight that much.
If you give me another color, I will do. Otherwise, I don't know. I'm sorry. Maybe on the recording, if you zoom, you will. I will read everything that I write. So we will work with F11. This is 1 to the 10. No, sorry, 1 to 10 with the sum. Okay. So in our case, P will be 11. T will be 2. P is a prime number. 11 indeed is a prime number. And T is 2. This means that we can commit polynomials of at most degree 2. Okay? And G is 2. G is the generator. Okay? And well, there are theorems in mathematics that says actually finding a generator of J modulus prime is really easy with the sum because every number co-prime with order is a generator. So in particular, to make things easy, G equal to will be our generator. And I'm sorry because I have to explain a lot of things, but don't worry. Okay, thank you. He's waiting patiently. Okay, but we need a painting as well. Don't forget because some of you will be a verifier and will need the painting. So I choose this painting. Simple, right? And actually it's a painting. It's amazing. But I mean, I want to make sure that everything is working well, and we will check the two properties of the paintings. Do you remember them? Non-divergent? Non-degenerate. Okay, close. Thank you. And the other one, and actually this is really important, bilinear. Okay, cool. You know. Well, checking the bilinearity means that if we take xy plus x2, comma, y, this is equal to and please believe me that this is like this. This is actually linearity, and if this also holds for y, this is bilinearity. Okay, and let's see. I mean, this thing here, what is? It is alpha equals 3. I will write what you have to do, and then you will do that. Okay. So we need the public parameters that are g. Here we don't have g to the alpha. We have alpha times g because we are not multiplying. We are summing. Okay. So we have g, alpha g, and alpha square g. Your turn. You have, I mean, when a g is, put whatever, and alpha 2. Oh my, it's alpha, alpha is 3, yeah. No, this is, okay. Don't worry. We're cool. Okay, cool. And if we do this mod 11, what we get? No. I mean 2 mod 11, 6 mod 11, yeah, 18 mod 11. This is the same, right? It is the same. No. Yeah, this is 6. 6 mod 11. Okay, cool. Perfect. Our trusted party has computed for us the public parameters. And please, before you leave, what you have to do? No. You don't have to sum them. You have generated. Thank you. Now yes, please. So nobody knew that alpha was 3. So I will give you only this. This is 2, this is 6, and this is 7. Okay? And this is G, this is alpha G, and this is alpha square G. Okay? So we don't need that. Okay. Now what? Who wants to commit a polynomial? Actually, if it's a woman or someone that identifies as a woman, it will be better. Because she will be Peggy. Nobody? Thank you. Please. What's your name? Nice to meet you. Okay. Well, again, no. Let's assume that you, of all the polynomials that you have got committed, you will commit this polynomial here of degree 2, because we can commit polynomials of the degree at most 2. The polynomial will be 3x squared plus 5x plus 7. Okay? And now I will write you what you should be computing, and we will compute together. Okay? And yeah, so the commitment of this will be this C, that, well, usually the notation of the field elements, when they are multiplied, they are like this, with these square brackets. So we need to compute that. And this is 3, and this element corresponds to alpha square G, and I will explain why. Alpha square G plus 5 alpha G plus 7G. Why G everywhere? Well, on the reals, when you are doing like 3 in reals, you are taking 1 as a generator. You really are doing 3 times G, and G is 1. So 3 dot 1 is 3. But here the generator is not 1, it's 2. So we need to, every time that we do a sum and an operation like this, we need to multiply by the generator to obtain the number on the field, on the field mod 11. Okay? This, like, I discovered this like this night. Exactly. Well, now your turn. You have 3, this expression. I need you to evaluate this expression. You have.
So we're changing this, right, and getting it to the equation.
Sorry?
So we're taking this.
Yeah. Exactly.
And getting it into the equation. Right. Is that true?
Yeah.
So this is C, right?
Yes, yeah. This is C. This is the commitment. This, you have, you have to take this, and you have to say, exactly.
This is 7, right? This is 18, and then we add all these.
Exactly, cool.
So this is 3 times 7.
Cool.
5 times, this is alpha G, so we calculate this and this, and this is 6. Okay, and then we have 7 times G. G was the first one, because we do not have this denominator. It's not like x so this is x to the power of 0, actually. So
She's nailing it.
so this is 7 times 2.
Cool.
This thing is 1 plus 30 plus 65.
Correct. Mod 11?
Okay, so this, now we have to do more, right?
Exactly. Because we don't like large numbers. We like small numbers.
Except that and we can, right?
Correct. Perfect. Oh my God. Please. Clapping. I'm really, no, don't run away. You're not done. You're not done. Okay? So, perfect. Put here that, I mean, the commitment is equal 10. And, exactly.
So now the verifier.
Exactly. And now we will pick a verifier. That will be Victor. Any Victor in the room? Sorry, you. Please. Jeff. Okay. Well, right now, what I need from you is to ask the prover, Peggy, to open this polynomial at a equals 1. So, you will say, hey, Peggy, give me the valuation of I equals 1. And then, for now, you rest. But it's technique. Okay? So, what are you going to do? We need to provide to the verifier with A equals 1 to phi of 1 and with the commitment of the C. And for now, we care about that. So, phi of 1, what is that? You have phi here.
Okay, so that means that x is 1.
Correct. X is 1. And here you don't have to mess with that. So you only need to put 1 here and sum.
So that's it. So I would have to power. So I would have to go to x to the power 2.
Well, 1 to the power 2 is 1 as well. So 3 times 1 is 3.
Great. 7 equals 15.
Mod 11.
Okay, so it's every time.
Every time.
Every time. 6. It's 4.
Cool.
You do
Perfect.
half.
Perfect. No. We're not done. Because, well, we have A is 1. Phi of A is 4. And now we need to do something hard. Okay? What we need to do? We need to divide polynomials. And the phi, if you recall, it was phi, the psi is phi of x minus phi of 1 divided by x minus 1. Okay? And I will do some computations for you. This is like 3x squared plus 5x plus 7 minus 4 divided by x minus 1. Okay? So you have to do this quotient. And I don't know how you divide the polynomials, but I'm doing like high school way. 3x squared plus 5x. 7 minus 4 is 3, mod 11 is 3 as well, plus 3, divided by x minus 1. And I'm running out of time, so I will do it fast, okay? This is not the purpose of this workshop. So, well, if you divide, it will be 3x plus 8, and this you can check that this perfectly divides this by this factor, okay? So, after all of this,
C of I
is 3x plus 8, okay? Psi of I is 3x plus 8. And then you are going to do the commitment, because we need to commit that. Do you remember how you commit the last one? Your turn.
the same way.
The same way, exactly. She's even following the notation. I love it. I love it. Okay. Well, she is doing the same expression as before, and yeah, we have 3 times the second parameter and 8 times the generator. And if she's doing well. Perfect, I mean, please. Awesome. Okay, so the commitment now, the commitment of the polynomial is 1. So now you have all the information, I mean you, Peggy, have all the information to send the commitment, well, the proof, to Victor, the verifier. So Victor, you now have the original commitment that I don't find it, 10. You have C equals 10, you have A equals 1, phi of A equals to 4, and you have this commitment that this is the proof. The proof is 1. Okay? And with that, honestly, you have to do the hardest part. No, don't worry. Exactly. Don't do that at home. Use Okay, let me check. 1, 4, 1, 2, and 10. Cool. But I remind you that G is 2, and these are the public parameters that you need. Okay? So, in order to be convinced that she is telling the truth, you need to compute 2 pairings. Okay? This pairing, remember, the pairing is this. X times y, that's all. Okay? Let's see, yeah. You have to compute this pairing. I mean, this is not the pairing that I show you, but this is easier to do. I mean, since you can play with the exponents and the things, whatever you want, you can find many expressions, and this, I think that is easier. You have to compute the pairing of the commitment original plus minus phi of I and the generator. You have to check if that is equals to this other pairing. I will help you. This is the similar expression of what I show you when the guy said, okay? And this, if you recall, this is like from here. When you want a field, an element of the field, you have to multiply it by the generator. Okay, so we want this value actually with minus, but we want this in the field, not in the real that we are used to. So in order to do that, you have to multiply it by G. This is why I put this. And this is why I put this 1. 1 by G is G. Here is only G. And this would be alpha G minus IG. Okay? And this will be minus phi of I. But minus phi of I is minus 4. What is minus 4 mod 11? This is like going back. It's 7. Okay? So what you have to do is compute that. E of phi the commitment plus 7, comma 1, and this is also E of the commitment. What is 10? What is that? 7 times what? Times 3. Plus 7 times 2, comma 1 times 1. 1 times what? Also 3. Also 3. 2, not 1. And if you do the computation, you will see that this is E of 24, comma 2, and 24 times 2 is 48, and 48 is 4. Mod 11. Okay? So the left hand side is 4. Let's see if the right hand side also is 4. Okay? Now E of, what is this?
1.
Is 1. Yeah. 1. And what is this? Here we have again minus I. I is 1. Minus 1 is going like 1 backwards. Is 10. Mod 11. 10 mod 11. So we have this is yeah. This is alpha. We don't have X here. This is alpha. This is alpha. Okay? I will explain you later. Okay? This is like the real thing that the pairing is doing. Okay? And yeah, we have 1, and this is alpha plus 10. And well, this you can put like alpha G plus 10G. And alpha G is 6.
Okay, so we exchange those like we did here.
Exactly the same.
That's what we connected. I think that's how you connect also that.
So we have here this like this, and this is 1, this is 6 plus 20, okay, and this is 26 times 1, which is 26, and this happens to be also 4 modulus on level, okay? So you
That's what we have. Yeah, so this was the left-hand side of the equation. That was also the right-hand side of the equation. So that matches, and then we're actually.
So
and
this way I verify.
and the verifier will say that.
Verified.
Thank you. Okay. Yeah, thank you. You can see it. Thank you a lot for your help. And, well, I said that, and with this I finish, I promise. Yeah, I said something like, please, Carlos, delete alpha. Why delete alpha? Actually, I have slides. Actually, yeah, I want to show because there is a good one. So if you don't delete alpha and alpha is leaked, then the prover can create false proofs that the verifier will accept, and this is like really dangerous. You know, I mean, the whole purpose of this is like even without trusting each other, you can be sure that the things are doing good. So here I also have an example, actually over this, where I will show you why this is dangerous. I will delete that. Okay, and let's recall that alpha was 3. Okay, And if alpha is 3, then the prover can do something like this. The prover can say, look, this polynomial looks cool, and I will commit you a commitment of this polynomial. But she can come up with another polynomial. For instance, I don't know, this g, that is 2x squared plus 7x plus 4, where phi of 3 is 43. Let's forget the mod element, okay? And t of 3 is also 43. So the commitment will be the same, but the polynomials are different. So with this, the prover can commit a polynomial and then change the polynomial, and the polynomial will and the commitment will match, but the polynomial is different. So she won't be able to. I mean, she's not going to prove that she knows the same polynomial. And yeah, please delete the toxic waste. that's the take-home message here. And I think that this is another example, but yeah, this is the same. This is what I show you. If the P knows somehow that alpha is 3, then P can commit this polynomial, which evaluates to 147, and can also commit this polynomial that also evaluates at 147. So the commitment of P1 is G to 147, that is also the polynomial for P2. So that's really dangerous, because it breaks the binding property. And well, that's all from my side. Thank you for staying with me till the end. I really appreciate it. If you like the things that I do, here are like my socials and this kind of stuff. And here you have a QR code about my research. Yeah, thank you for your time.